Hi, College Algebra. What we're going to be doing today is section 3.3, zeros of polynomial functions. And what we're going to be looking at is this list that I have right here of 5 things. And all 5 of these things rely heavily on what we learned in the previous section that has to do with synthetic division. So let's go ahead and get started. Here's our factor theorem for polynomials. And this is what it states. For any polynomial function f of x, x minus k is a factor of the polynomial if and only if f of k equals 0. Well, what we can take from this is kind of what we did in the last section with testing for potential zeros. Whenever we test for potential zeros, what we are looking at is we're trying to figure out, let me write some, trying to figure out if our k value, well, we're given x equals k, we're trying to figure out if that value is a 0 of our polynomial. And this factor theorem is pretty much the same thing. If k equals 0 is a 0 of our polynomial function, then also x minus k is a factor of our function. Because if you work this problem backwards, say solve for 0, you would get x equals k. So same thing as we're doing yesterday in finding potential zeros. We are just finding factors of our polynomials. So here we go. We're going to just do the same exact thing that we were doing yesterday with our synthetic division. This thing is asking us to find if x plus 4 is a factor of this polynomial that we're given. Well, like I said, in synthetic division, take this value right here. If we want to test that this is a factor, well then test to see if it is a potential 0. So test to see if x equals negative 4 is a 0 of our polynomial. So use the synthetic division. Bring down all coefficients. Oh, we're going to have a 0 here. We're missing that x cubed term. Now just follow the steps of our synthetic division process. Bring down the 3, multiply negative 4 to 3, get negative 12. Add together, multiply these two, get positive 48. Add together, multiply negative 4 to 0, add, multiply negative 4 to 8, get negative 32, and that means our remainder here is 0, which means if we get a remainder of 0, just like yesterday, if we got a remainder of 0 for this potential 0, then it was a 0. But this case, it means that x plus 4 is a factor of our polynomial. And this is how we're going to end up factoring our big polynomials, is by testing potential zeros or testing for potential factors and using synthetic division to help us out in that process. So let's look at something else. Now, let's do this again. It's asking, is x plus 4 a factor? So again, let's do this process. So again, we're going to say test for this as a potential 0. And then if it is a 0, then x plus 4 is a factor. Alright, now all of my coefficients are 1, 6, 11, 12, 5, and negative 20. Alright, now synthetic division process. Bring down the first number, multiply. add together, multiply, add together, multiply again, get a 0, multiply, we get a 0, and then adding, we get a 5, and now multiplying that together, we get a negative 20, which means we get a remainder of negative 40. So, since our remainder did not end up being 0, this means that negative 4, or f of negative 4, does not equal 0, and x plus 4 is not a factor. Okay, I think y'all get the gist of this now. So, now we are asked to factor f of x equals this big long polynomial into linear factors if 5 is a 0 of f. So what it's giving us, it says we are given that 5 is a 0. Now factor this polynomial, knowing that fact. So if 5 is a factor, if 5 is a 0, then x minus 5 is going to be one of our factors of this polynomial up here. So let's do the synthetic division process and take out this factor and rewrite our polynomial. And we'll see what we do next after that. So take out the 5. Using synthetic division. Okay, now we're going to get 6, negative 7, negative 3, and then 15. See, we ended up with remainder 0. So if we are given that 5 is a 0 of our function, then we should know automatically, well, our remainder is going to be 0. If our remainder isn't 0, we did something wrong in our division process. Okay, so how we rewrite this is our f of x is now equal to our factor that we just factored out times this right here. And this right here becomes just like we did in our synthetic division. We're going to write it out. Remember that our variable of x, the power on it, is going to be 1 less when we divide a factor out. So it's going to be squared, and then it goes in descending order. So minus 7x minus 3. And there, we factored out a 5, but now it says to divide into linear factors. So factor this all completely. Well, this right here, what we have left in our function to factor is this right here. And that is a quadratic. We should know how to factor quadratics. We can use the Berry method in this to help us factor this quadratic that we have left over. But I'm just going to write down the factors because I know what it factors out to. Please tell me in class if y'all need help with that Berry method all over again. I know we can forget that sometimes. Okay, so this factors out to 2x minus 3 and 3x minus 1. Alright, so there is our function that we began with up here, completely factored out into linear factors. And that's what this section here is mainly about, is factoring everything into linear factors. And then the next process we're going to be doing is finding all of our zeros of our function. And I'll show you that here in just a bit. Before we get into finding zeros of our polynomial functions, we're going to learn something called the rational zero theorem. What this rational zero theorem does, it helps us narrow down the list of all real numbers to a list of rational zeros that we can test as potential zeros. So I'm going to show you in an example how to come up with our rational zeros. Alright, so here's our example that's going to help us in figuring out this rational zero theorem, and also it's going to help us come up with possible zeros for our function that we have right here. So let's use that theorem. How we use that theorem is we come up with our p's and our q's. And where those values come from, our values of p come from all factors of 4, or just the constant term, the term that doesn't have an x value on it. And then where the factors of q come from are this leading coefficient, so 8 in this case. So p is going to be our factors of 4. And we're going to list those. Q is going to be factors of 8. And we're going to list those factors. And whenever we're listing factors, we're also going to list all possible factors, meaning like -1 times -4, that adds up to +4. So we have to list all positive and negative values of our numbers, just like this. So positive and -1 is going to be a factor, and so is ±2 and ±4. Okay, let's do the same thing with 8. Gonna have ±1, ±2, ±4, and 8. Now to put together these factors to come up with our possible rational zeros, so you write that all out. How we're going to come up with that is we're going to place all of our combinations together of p over q. So just like this. We're going to say 1 over 1, and then 1 over 2, 1 over 4, and then 1 over 8. And then start all over again with the value of 2. Say 2 over 1, 2 over 2, 2 over 4, 2 over 8. And then just keep on going through our list until all of the combinations have been covered. But we're not going to write down every single one of those. We're going to write down just the rational ones that are reduced, all the fractions that are reduced. And we're not going to repeat any. Because, like I said, whenever we go through the list, we're going to have 1 over 1. Well, that's 1. And then we're going to have, again, when you get to 2, we're going to have 2 over 2. Well, that's 1 also. So we're not going to repeat that number. Let's get started. We have 1 over 1, just 1. Then we have 1 over 2. And 1 over 4. And 1 over 8. Okay, now let's start with 2. We have 2 over 1. And then 2 over 2, like I said, that's 1, so we're not going to repeat ourselves. And 2 over 4, that's 1/2. And then 2 over 8, that's 1/4, so we're not going to repeat that. Now we're going to go to 4. 4 over 1, well, we don't have that number listed, so let's list it. And then 4 over 2, that's 2. 4 over 4, That's 1, and 4 over 8. That's 1/2. So there we go. We have our list of possible rational zeros, which means this is a list of potential zeros. So whenever we go to use our synthetic division to figure out possible factors of this polynomial, because we're going to end up factoring it completely, and then finding the zeros, the actual zeros of the polynomial, well, we're going to be using this list that we just came up with for possible zeros in testing with our synthetic division. So let's do that with this function here that we're given. We are going to come up with factors of our function and then go on to finding zeros. Alright, now that we've come up with all of our possible zeros, what we're going to do, like I said, is factor this function and find all of the linear factors. And now that we've have a list, a very narrowed down list actually, to help us in finding these zeros, now we just have to use trial and error with that list. And this is how we're going to do it. We're going to use our synthetic division. So let's test 1 as a potential zero. And that means x minus 1 is a potential factor. Whoa, it's too big. Okay, 1. And list all of the coefficients. So these numbers here. And now do the process. Okay, now going through this, what we're going to see down here at the end, oops, not 33, 34, is that we are not going to end up with a remainder of 0, which means 1 is not a factor. Okay, so this 1 is not a factor. Okay, let's test -1. Usually I like to start out with the smaller numbers and not the fraction ones. That's why I'm testing 1 and -1. Many times that will end up with a good result for us. So let's test -1. So 8, 6, -27, 11, 4. Okay, let's do our synthetic division process to get us a good result here. Okay, looking good. Yes, we have a factor. So -1 is a factor, which means we can factor this polynomial out into this right here. We have -1 as a factor, which means x plus 1 is a factor. And what's left over from factoring out a -1 is this right here. Use this. So 8x. So the power is going to be 1 less than what we started out with up here. So 3 minus 34x squared plus 7x plus 4. Okay, so now let's keep on factoring. Okay, so what we're going to do to factor out the rest of this is we're going to factor just this portion right here. And if I had enough room on the previous slide, this is what I would have done. I would have kept going from what was left over from the previous synthetic division. So you had left over this right here. And I would have just put this right here, this division thing, and my next potential 0 on the outside right here. And this time, for all of our potential zeros, we can sometimes narrow the list down by finding possible factors of 8 and 4, but we already have that list. It stays the same. Sometimes it doesn't stay the same. Sometimes these numbers here and here change, and we can narrow a list down even further. But this case, we can't. At this point, we can say, let's try a factor of 2 or try a factor of 4. It's just a guessing game at this point. But I'm going to try a factor of 4. And sometimes you can visually see what factor is going to work out. And the reason I say 4, I think is going to work out is because, well, 4 times 8, that gives us 32. Then we're going to get a -2, -8, and then we should end up with a 0. So let's try that. Bring down the 8. Like I said, 32. Gives us -2, -8, -1, -4. Voila. There's a remainder of 0, which means 4 is a factor. And what this means is our function, f of x, is now factored out into our previous factor we just figured out, the x plus 1. And now this one, x minus 4. Always change the sign that is on this right here. Since it was positive 4, change it to minus sign here in our factor. And then where we come up with the rest of it is this right here. So 8, subtract power from this right here. So 3 becomes 2, and minus, so bring down these, 2, and then -1, bring that one down. And there we have a quadratic, and we should know how to factor quadratics, like I stated before. And this right here, this quadratic will factor out. Let me rewrite these factors first. Into this. So again, use that very method if you need to. If you don't have to, then don't. There it is. That is our linear factors of our function. And now if you are asked to find all the zeros of our function, this is how you would do it. You have all your linear factors. Now set your equation equal to 0, which means we're going to set each and every single one of these factors equal to 0 and solve for all of our x values. So all of our x values, let's write that. We're going to have x equals, from this one, we're going to have a -1. From this one, we're going to get a 4. This one's going to give us a 1/2. And then this one is going to give us a -1/4. See, this list right here is all of these actual zeros that we found we're in that list of possible zeros. That is going to be the case every single time. All right, let's do something else. All right, so here is something called the fundamental theorem of algebra, which states every function defined by a polynomial of degree 1 or more has at least one complex zero. This is very true. Don't just disregard this theorem. Take it to mean something. What this means is, well, if I have a polynomial that's degree 1, and I've shown y'all degrees, degree 1 means the function has, like, let's just give you an example, x plus 2. This function is of degree 1. It's a linear function. Degree comes from the highest power on x. And then functions like, if I had a function that said x squared plus 2x plus 1, well, the degree on this polynomial is 2. And what this fundamental theorem of algebra is stating, there is going to be at least one or more complex zero that you can find in this function that you're given. So every function has one or more complex zeros. And what you can take from this also is it has one but no more than the degree of the function. So this one has one or two factors or zeros. And polynomial of degree 3 will have at least one but no more than 3 potential or zeros. Okay, so let's use that. Okay, so here are one of the ways that we're going to actually use the fundamental theorem of algebra. And it's going to be in the process of coming up with a function given all of the zeros. So we're going to work our way backwards. Usually, so far, what we've been given is the function, and we're asked to find the zeros. But in this, what we're going to be using is we're going to be given the zeros of the function, and we're going to work our way backwards to find what our function is. And this is going to be kind of the formula that we use for our coming up with our functions. So if we're given, okay, our polynomial is degree 4. Well, we're going to have 4 factors in this polynomial, and it's going to follow this. This is our kind of a formula here for us. We have our a times our first factor, and then our second, then it keeps going, fourth, third and fourth, and our x values that we are given are going to go in here, as in case of 1, case of 2, 3, and 4. So let's look at a example. Okay, well, kind of already shown you this. The number of zero theorem. Function defined by a polynomial of degree n has at most n distinct zeros. So that's what I was stating before in the fundamental theorem of algebra. But fundamental theorem of algebra says that a polynomial of degree 1 or more will have at least 1 or more zeros. And then this right here states that, well, if it's degree n, it's going to have no more than the n zeros or n factors. Okay. So here's the example that I was talking about that we're going to look at. And we're going to find a function, f defined by a polynomial of degree 3. So that's very important. We have degree 3. And has zeros of -3, -2, 5, and then we know a value of f of x equals 6, so f of -1 equals 6. I'm going to use all of that information to come up with our function. And like I said, use that kind of formula thing that we had. So f of x is going to equal a times our x minus case of 1, case of 2, and in this case, we're going to stop at case of 3, because we are given 3 zeros and that the degree is 3, so there's no more than 3 zeros. Now we're going to plug in what we know. So negative 3 needs to go here, negative 2, negative 5. And then we're going to use this fact right here to come up with our value of a. Okay, so let's do this process. X, this is going to be plus 3. Now this is going to be plus 2. And minus 5. Alright, so before we start multiplying all of these factors out together, what we're going to do is find this value of a that we have. We're going to be using the fact that f of negative 1 is equal to 6. So, in for f of negative 1, which is going to be 6, we're going to replace all of our values of x with negative 1. So negative 1 here, negative 1 there, and negative 1 here. Now, find that value of a. Well, that value of a is going to equal negative 1/2. And now, kind of to save us on time, the next step is replace this value of a, that's negative 1/2, in for a, and rewrite your whole function just like this. And what we're going to do is multiply everything out. If you need me to show you in person how to multiply all of these factors together, please let me know in class and I will help you with that. But like I said, to save us on time on this video, I'm going to say f of x equals this right here, negative 1/2 x cubed plus 19 over 2 x plus 15. And there we go. That is our function of f. And with all three of these as zeros, and f of negative 1 equals 6. Okay, now I'm going to maybe show you another one. Let's see. Alright, so yes, I am going to show you another one. It says, find a function f defined by a polynomial of degree 3 that has zeros 4 of multiplicity 3 and f of 2 equals negative 24. Well, the meaning of multiplicity means whenever it says I have a zero of some number of multiplicity and then it gives you another number, well, that means I have the factor of 4, or the 0 of 4, 3 times. And this is how you're going to write it. So we're finding f of x. It has degree 3, meaning it's going to have 3 factors. And we need to have a value of a. And our 3 factors are going to be the same thing. X minus 4, x minus 4, and x minus 4. Okay? Or we can say this right here. X minus 4 to the third. There we go. So now what I'm going to do is find my value of a. I'm going to say, well, f of 2 is equal to a times 2 minus 4 cubed. F of 2, well, that's negative 24, because that's what we're given. And this right here is, negative 8. Negative 8a. And a is equal to 3. So now what we do is plug that value of a back in. F of x equals 3 times x minus 4 cubed. And if we were to multiply all of these factors out and then distribute that 3 across everything, this is what we're going to get. 3x cubed minus 36x squared plus 144x minus 192. And we are done. Alright, another theorem. Sorry, we are learning about many theorems in this section, but they're there for a reason. Anyway, conjugate zero theorem is about if we're given, just like in the previous slide, we were given that our polynomial was degree whatever, 3, and then we're given, our zeros, our 3 zeros. Well, sometimes we could be given, we have a polynomial of degree 3, and the zeros are 3i and negative 2. Well, they only gave us 2 zeros. What's the third one? So how we're going to come up with that is this conjugate zero theorem. If we are given a complex zero, like 3i, or even something like the square root of 3, the conjugates of these are going to be the opposites, like the negatives of these. So the other zero for this example right here that I have is going to be negative 3i. And if you were given this right here as a complex zero, then the conjugate of the other zero of your function is going to be negative square root of 3. And this applies to even more complex numbers that have real numbers along with it. Say you were given the zero, say you were given this is a zero, that 1 plus 2i was a 0. Well, the conjugate of it, 1 minus 2i, is also a 0. So when you get to problems like that and you think, oh, they forgot to list another 0, well, look back through your list. If one of them is a complex 0, take the conjugate of it, there's your third 0, or your other 0 that you think you're missing. Okay, so here's an example of what I was talking about. It asks us to find a polynomial function of least degree having only real coefficients and zeros at negative 4 and 3 minus I. Well, we're not going to have i's in our functions at all. Whenever we multiply everything out, the i's should have disappeared. We should have all real numbers as coefficients. So that would be a very big clue that if we have something in our function that we have figured out, we're saying, oh, this is our function, well, and it has I in it, sorry, that's not the correct function. Because we forgot to say that if 3 minus I is a factor or a 0, then 3 plus I is also a 0 because of that complex, or that conjugate zero theorem that we just looked at. Okay, so now let's find this. Now this can get complicated whenever we multiply, so I'm going to show you this one. f of x equals. Now, whenever it says find a polynomial function of least degree, well, we don't need to include that a on the outside. We're just going to list all of our factors that we're given, forgetting about the a. So x plus 4 is one of our factors, and x minus, and put this in parentheses, 3 minus I, and x minus 3 plus I. There you go. There's our function, but like I said, we're going to multiply this out. And what I'm going to do is this right here. This will work for every single complex zero that you have. I'm going to say, let's switch where our parentheses are. I'm going to put together x minus 3, then minus I out here, and x, whoops, x minus 3 plus I. Okay. Now, when we multiply these last two in our parentheses right here, these two factors, what we're going to do is multiply together the first two terms and the last two terms. In conjugates, that's all you have to do. You don't have to FOIL. You just multiply the first two terms and the last two terms together. And this is what we're going to get. We're going to get x minus 3 squared minus I squared. And I squared, you should know that, is negative 1, but it's minus I squared, so it's going to be plus 1. This right here should be fairly easy for you to multiply out. I've shown y'all a quick process of multiplying that out before. It's going to be x squared minus 6x plus 9, then plus 1. So now we have this, x squared minus 6x plus 10. And now multiply everything out. So we're going to multiply the x to the x squared, x to the 6, and x to the 10. And then do the process all over again, but with our 4. 4 to the x squared, 4 to the negative 6x, and 4 to the 10. Then combine all of our like terms together, and this is what we're going to get. X cubed minus 2x squared minus 14x plus 40. And there we go. That's the function we are looking for, or the polynomial function we're looking for, of least degree, having real coefficients and zeros at negative 4 and 3 minus I, and then 3 plus I we had to add in there. Okay. Okay, one more example I believe we have. It tells us to find all zeros of this function here, given that 2 plus I is a 0. Well, I've shown you before how to use synthetic division on complex zeros such as this. We're going to do it again. But remember the conjugate theorem that we just looked at, if 2 plus I is a 0, then 2 minus I is also going to be a 0. And that's what we're using in this example here. So let's use 2 plus I and figure this out. This is going to be kind of long. Putting more space in here because of the complex 0 that we're having to use and subtract. Okay, so bring down the 1. 1 times the 2 plus I, we get 2 plus I. Add together those things, we get 1 plus I. Now, multiply together 2 plus I and 1 plus I. What we're going to get is a 1 plus 3i. Add together the real terms, we get negative 16 plus 3i. Now put together the 2i, say 2i or 2 plus I times negative 16 plus 3i. I'll show you all how to use your calculator for these. That will make this process a lot quicker. So remind me of that in class. And then put together 55 and this by adding, get 20 minus 10i. And then finally, the 2 plus I and 20 minus 10i multiply together does give us 50, which gives us remainder 0. That's what we're looking for because 2 plus I is a 0. Therefore, the remainder must be 0. Now we're going to continue this process with knowing this fact right here, that if 2 plus I is a 0, then 2 minus I is a 0 also. Oops, not 1. C. I. Okay, so let's continue the process. Bring down the 1, multiply, we get, what do we get here? 3. 2 minus I, we get a 3 here. And then we multiply 2 minus I times the 3, 6 minus 3i, add together. Then 2 minus I times the 10, we get negative 20 minus 10i, which is 0 remainder, and it should be. Now, what we have left over here is, let me move this up. What we have left over is this function right here. We have the factors. Oops, need an equal sign there. X minus 2 minus I. Actually, let's plus first. And x minus 2 plus I. Oh, sorry, minus. And then what's left over is comes from here. The 1. So we factored out 2 zeros, or 2 factors. So we're going to subtract 2 from our exponent of 4 to come up with the rest of our polynomial. So 1x squared plus 3x minus 10. Because it's descending order, just go from the powers to 1, none. And then we can factor out this right here into x plus 5 and x minus 2. And then let's bring down these as factors also, multiplying those all together. Now, it says find all zeros. Well, here are all of the zeros. We have we're going to list x equals 2 plus I, 2 minus I, and then the last two zeros come from this right here. So minus 5 and positive 2. There we have it. And we are done. So hope you didn't sit here too long. I'm sorry if it became long. But anyway, we are done. And if you have any more questions about multiplication and stuff like that that I kind of skipped around on, please let me know in class, and I will see you later. Bye, everybody.